And our last speaker is Kotlarz, who was also asking the question. And hopefully he will be able to share his screen very soon and move us to the ocean worlds. And perfect, almost there.
Can you see my screen?
I can. Very interesting. Okay, perfect. And I will switch off myself again. When it will be about 11 to 13 minutes, I will let you know that you are at this time point.
Thanks. Okay. Hi, my name is Kotlarz. I'm an astronomer and I work in the Institute of Aviation in Warsaw, Poland. Today I will present the results of our work on the development of techniques for detecting microbial component in water plants, geysers, such as those present on Enceladus or, for example, smaller on Europa. This project was a common work of the Institute of Aviation, Institute of Biochemistry and Biophysics, Space Research Center, and University of Warsaw. Now I want to present this topic on the example of Enceladus, which is a small satellite of Saturn. It has diameter about 500 kilometers and it's made primarily of a gravel core and of course water. And because the distance between the Sun and Saturn is about 10 astronomical units, we have about 100 times smaller intensity of sunlight. And if we look at the Enceladus from the outside, we can see primarily just an ice shield. Well, all of the water present on the Enceladus should be just ice, but we have also thermal activity at the bottom of the ocean, especially around Enceladus South Pole. As a result of this process around this South Pole, we can see some kind of scratches made by a tiger's paw, something like this. And these are several kilometers wide furrows from which ocean water escapes to the space. These furrows can be seen very well also in thermal images and also the heating process itself is very well visible, as you can see on the picture. Observations of the tiger stripes were made by Cassini probe. In these images, we can see structures very similar to our planet's oceanic rifts. And the reason of these amazing structures, which are some kind of evidence of the geological activity of this frozen world, may be, in example, hydrothermal vents at the bottom of the ocean. And this well-known diagram shows hypothetical cross-section throughout the ocean. Here we see an ocean with depth of, according to various estimates, from about 10 to 70 kilometers. And according to some of the ice directly at the heating site it might be only 5 kilometers. What is very important from the potential biology point of view, the ocean is very salty and its pH is about 11-12. So there are several hypotheses why we have such high pH. Perhaps it's a consequence of geological process, serpentinization of olivine, which may occur on the ocean bottom. And On this slide, we can see the chemistry of this process, but I wanted to point out that on our planet, we are dealing with a very similar one of the bottom of the Atlantic Ocean in a place called Lost City. And on this beautiful film made during the expedition from the University of Washington, we can see places where organisms of the Methanosarcinales strain are living with temperatures above 60, 70, 80 degrees. And they are living around hydrothermal vents during the olivine serpentinization process. It's important that they form dense biofilm in those places. Okay, and this biofilm contains about 2 million to 100, 300 million cells in milliliter in areas that are flooded with hydrothermal. And a lot of organisms in Lost City have adapted to temperatures around even 90 degrees and pH above 9. Okay, Lost City is some kind of analog of Enceladus ocean, and now let's back to this satellite. Here you can see chemical composition of geysers, and Cassini has found, of course, water, carbon dioxide, methane, also probably molecular hydrogen and other compounds. And methane and molecular hydrogen are products of this process of serpentinization that occurs also in Lost City. Okay, and our scope of research right now, we were trying to investigate 4 types of areas where we could find evidences for life and connected with those areas processes. So the bottom, of course, the bottom of the ocean around hydrothermal vents, surface of the ocean, surface of ice very close to the plum sources, where heavier particles fall from the interior, and geysers, of course. So in our project, we selected. Okay, so first we have collected samples of our model organisms, bacteria and methanogenic archaea, and we were working on 6 different model organisms. First, we collected spectral data in visible and infrared light ranges. And because we were trying first to detect pigments, we also collected multispectral images of suspensions in water. So here you can see example spectral measurements, and you can see that they differ from the sample with the analog of the ocean itself in laboratory conditions. But after experiments, we saw that those differences were often statistically insignificant. So this first approach with pigments detection failed. Then we tried to figure out where we should look for those 6 model organisms in geysers. And for this purpose, we developed kinetic model for the ocean and second model for geysers. And here you can see model for the ocean. And according to particle in cell technique, we have implemented gravity of Enceladus, viscosity, etc. All of those forces then could move particles in the ocean. And our second model was for geysers. And here you can see 4 types of biotic cell particles. 2 types are for small particles below 1 micrometer, like cells of archaea. And 2 are analogs for cells like bacteria. They differ also by initial escape velocity. Okay. And here you can see results. And what is important that if we assume density of cells like in Lost City, the density of cells at the top of the ocean, so there where geysers are forming, are about 9,000 cells per micrometer. And here you can see a paper of Caroline Polko's paper. And
sorry,
there's group.
Sorry, Jan, I'm not sure if it's me or if the slide is still on the one of the previous ones called spectral data. I think that it's not moving your presentation. Can you maybe stop sharing and start it again?
Okay. Okay, can you see my screen?
Yes, like the infinity. Okay, yes, we moved. Perfect. Gone.
Okay, thanks. Okay.
Just do yes, the full screen. Okay, awesome.
Okay, so here you can see that our results are very similar to Caroline Polko's team estimations, about 10,000 cells per milliliter at the ocean top. Okay, and here our results for plumes. And you can see, which is very important, that the density of cells differ according to their size or mass. Okay, is this maximum height of these cells okay for detection? Well, we can plot the result here on the one of the images from Cassini, and you can see that those big cells are not escaping to the height of, in example, Cassini pass throughout the plume. Okay, and here for the X and Y direction also. So we can see that we should find the look for these cells somewhere around plume sources. And another plot here.
I think it's still not moving. I'm very sorry.
Oh, sorry. I don't know why.
Okay, now it just moved very quickly.
Sorry.
So, yeah, sorry. The slides just very something
Okay.
is not right. I'm not sure what is the problem, but let's try to fix it. Okay.
Okay, so we failed with pigments, but we were trying to analyze scattering models according to mere solutions for Maxwell equations. And here you can see that scattering intensity depends on the angle of scattering when we have light wavelength and particle size in the same size. So when we have cells around 1 micrometer and light around 1 micrometer, we can use this model here. So when we are passing throughout the plume, like Cassini, we should see those fluctuations of the scattered light intensity. So here we have developed two models. First for ocean analog without our model organisms, and second with model organisms. And we've done some experiment in the vacuum chamber. And here you can see that the intensity of scattered light in few wavelengths were different in time. And if we analyze those scattering intensities and classify to some phases, we have 4 phases of this experiment. And we can plot spectral signatures just only in 5 or 6 wavelengths, but some spectral signatures like in astronomy of each phase. And if we correlate those signatures with models, we can see that we have first 2 phases without cells escaping from the samples, and phase 3 and phase 4 when we can see that there are cells which are escaping. It's very important that between phase 2 and 3 we have something like bubble scrubbing, which is also described in Caroline Porco's paper. And those cells were escaping just after this bubble scrubbing, when bubble scrubbing occurs. So right now our team is working not on plumes, but we are looking for some surface biosignatures for Enceladus and Europa future missions. Here you can see literature, and thank you very much.
Great, thank you a lot. And that was a very interesting question. And I can see that Tomek has the same question as I do, which is, what is bubble scrubbing?
Okay, bubble scrubbing is, if you can see my screen.
Right now we are at the summary.
Okay, one moment. Okay.
Nope. Oh, okay. Yes. Good.
Yes. So this is bubble scrubbing effect. So when we have bubbles in the water, as Caroline Porco wrote in her paper, it might help to escape for heavier particles from the ocean. And our scope wasn't to confirm this assumption, but we confirmed that we saw we were detecting those cells after bubble scrubbing.
Very cool. So how, like, I'm wondering how much of the cells do you have to have in the material in order to be detectable with your method? And is it
okay, so in our experiment it was about 10 to 8 per 1 milliliter. So it was very dense experiment with dense sample. Okay, but our goal is to detect about 1,000, maybe 10,000 cells per 1 milliliter. So it's not very easy.
Yes.
And I forgot to say that we have success just for 2 strains, and we were testing 6 strains. So it's not very easy to detect them.
So what's the difference between those strains and other ones? Like, why the ones are easy to detect and other aren't?
Probably size, and second, probably we were detecting not single cells, but fragments of biofilm. So those strains which are forming biofilms, we were the detection were positive, but for the others not.
Okay, so big cells forming biofilms are easier to detect than small ones that hang out by themselves. Okay, good to know. Let's hope the microorganisms are social. Or at least forming biofilms. Anyway, bad jokes from geologists trying to speak about biology. So anyway, thank you very much. Very interesting presentation.